Here we want to pick up where we left off with our Intro to Excel lab, and we want to now look at how to fit various sets of data. So we have 4 data sets here, and I'm just going to highlight the first cell, and we're just going to plot all 4 of these. All right, we're just going to plot all 4 of these. And I'm going to shrink the plots so that we can more or less fit them all on one page here. We're just going to plot all of them. So again, the goal is to find the function that that minimizes the so-called R squared value. All right, we want to find the function that minimizes the R squared value, and that is the function that best fits the data. Now again, avoid polynomials, and I'll show you why. I'll actually show you an explicit example of why we want to avoid polynomials. Because you can always get arbitrarily close, an arbitrarily good fit with a polynomial. Now, Excel will only fit up to 6 orders on your polynomials, but that's still high enough that it will often be better than most other trends. So, for example, let's look at this first set of data here. And when I bring up the Add Trendline menu, okay, of course it's going to be linear, and I'm going to display the equation on the chart and the R squared value, and notice how good that fit is. 0.94 is not a horrible fit at all, but watch what happens if I choose logarithmic. Okay, it gets a little bit better. In fact, quite a bit better, really. So the question now is this a logarithmic trend? Well, it could be, but what happens when I choose exponential? Oh, wow, look at that R squared value. It shoots way up there. What about a power series? 0.904, not really that great. But watch what happens when I choose polynomial, okay? 0.9988. That automatically is better than the exponential, all right? And as I choose higher terms, I'm going to get better, all right? So as I go up to 6 terms, I've now gotten 0.9992, all right? And Excel only goes to order 6. It doesn't fit anything higher than that. But if you had a sophisticated computer program, you could choose an arbitrarily high amount and get an R squared of 1. All right, so that's why we don't like to use polynomials unless theory specifies that we should. So for now, for this exercise, we're going to avoid the polynomial and just look at exponential, linear, logarithmic, and power. And it looks like the exponential wins the day here with the 0.995. Now what about this particular chart? Well, again, the linear, if I display the equation and the R squared value, definitely not bad, 0.9789. Exponential is actually a very poor fit comparatively, 0.8745. Logarithmic is even worse, 0.811. But a power, wow, seems to fit it quite nicely. So we would conclude that more than likely that this is a power function. So then we go up to this data up here, and sorry about that. We come to add trendline and display equation on chart, display R squared value, and if I choose exponential, it gets much worse. Logarithmic is worse, and my power series is not bad, but it's not as good as my linear. So therefore, I conclude that this is linear. And let me pull this last chart up. Now, you might think that this is a linear line until you see this data point right down here. So let's go to add trend line. And notice now exponential is blanked out and the power is blanked out, and that's because of this data point down here. An exponential function you cannot have below the y-axis, right? You cannot achieve a negative number by taking an exponential, nor a power. So we're really restricted to linear and logarithmic here. So we're going to display the equation on our chart and display the r² value. And this is our result. But what if we choose a logarithmic trend? Wow, look at that. So the difference between the two is pretty clear. The logarithmic trend captures the essence of the data, where the linear trend gets the bulk of the data, but not all of it, right? So then we would conclude that more than likely this is a logarithmic trend. All right, so that is what we were after in the fitting. Now let's move to the density. All right, we'll actually use an example from some of the actual homework that was turned in. Okay, so I don't remember whose data set this was, but they measured the length of their box to be 13.7 centimeters, the width to be 13.6, and the height to be 20.3. And they assigned an uncertainty of about 0.5 centimeters to each. Now there's something to note here. Remember, in the text it says your uncertainty must match the number of decimal points as your measurement. So here I have 1 decimal point, so my uncertainty can only contain 1 decimal point. All right, and your uncertainty is just your best guess as to how much you are off. So if I have a really good measuring device, I may only be off a couple of millimeters as opposed to half of a millimeter. Or I'm sorry, half of a centimeter rather. 0.5 centimeters is 5 millimeters. So here we're claiming that we know this measurement to about half of a centimeter. And same thing goes for these other two measurements. If I have a really good meter stick and really sharp edges on my box, I may be able to say, I may know this to within just a couple of millimeters. Whereas if I have rounded edges and my meter stick's not that good, or it doesn't have millimeter markings, then I really have to do some estimation here. Now the volume itself, right, we're going to calculate the volume, and the volume is equal to the length times the width times the height, and here we're going to get a number. Okay, now let's interpret this number, 3,782.296, and this is in cubic centimeters. But all of my measurements here only have 3 significant digits. So I can only keep 3 significant digits here. So I need to round this to 3 significant digits. That would be 3,780. So I'm going to round this to 3,780. Okay? So that's my volume. And I've already got the formulas in here, so don't worry about those. Now, what about the uncertainty on my volume? Well, let's go back to one of the documents that you have in the Getting Started tab, if it'll open up for me here. It might take just a minute. Let's come back over here. It's not responding. That's not good. Oh, here we go. Oh, come on. Okay. So really, this is what we're after. Okay. This is what we're after. If I have a quantity that is the product of multiplication, then the uncertainty on that is going to be equal to the quantity itself times the square root of all of this stuff, right? And so that's the formula that I need to put into Excel. So I'm not sure what Word is doing right now. It's kind of going crazy on me, so pardon me while I back out of that. So the equals in here are the uncertainty on my x measurement divided by the x measurement, plus the uncertainty on my y measurement divided by my y measurement. And look at how these are also squared, and then I take the square root of the whole thing. And this looks a lot like the Pythagorean theorem, and in reality it's related to it. So I need to type in a formula in Excel that does the same thing. So my formula is going to look like this. I'm going to take my volume measurement and multiply that by the square root of my uncertainty in my length divided by my length, quantity squared, and that represents this first term, the uncertainty on my length divided by my length, and then this would be the uncertainty in my width divided by my width, and I'm going to also square that. And then I'm going to add one more term. It doesn't matter as long as your overall result, z, is just a simple product of multiplication and or division, then I can just keep adding terms in this square root. So this is one more term, the uncertainty in my height, divided by my height, quantity squared, and then I'm going to close off the square root bracket, and I'm going to get a result. Now, once again, I have to match the decimal places in my measurement and my result. So I would actually report this measurement as 3,780 cubic centimeters plus or minus this number rounded to no decimals. So that's going to be 217. So that means that I know my measurement to within about 217 cubic centimeters or so. Now the box was listed as being 1,530 grams, which is 1.530 kilograms. All right, so I'm actually going to change that number. Well, we'll leave it in grams per cubic meter, or cubic centimeter rather. All right, we'll leave it in grams per cubic centimeter. And our uncertainty, we estimate it to be about 5 grams. We would like to think the manufacturer is good. But they're probably not perfect. So the mass of each individual box that comes off the assembly line may be a little slightly different. Now, the density itself is just equal to the mass divided by the volume, and that's the formula that we have in here, right? The mass, F2, divided by the volume, D2. Now, the uncertainty in my density is the same thing as before. Notice that the formulas for uncertainty when I multiply and divide are the exact same. And so what I'm going to do is take the uncertainty in my volume divided by my volume plus the uncertainty in my mass divided by my mass, square those quantities, add them up, and take the square root. And this is what I get. Now, once again, this number is the result of a number with 3 significant figures here and 3 significant figures here, so I can only keep 3 significant figures here. So I would report this number as 0.405. And I need to match that number of decimal points with my uncertainty, so I'm going to take this out to 3 decimal points, 0.023. So now I know the density of my box is 0.405 grams per cubic centimeter, plus or minus 0.023. So it really could be anywhere between 0.428 or whatever, 0.405 minus 0.023. I'm not going to do the math in my head, but you can subtract those two numbers and that would be your lower bound. And so that is how you actually calculate the uncertainty in measurements like volume and density using those formulas in the document in the introductory materials. Okay, so if you have any questions, don't hesitate to let me know, but I did want to show you explicitly how that was done so that as we move forward, you can do it yourself and correctly. All right, we will see you next time.